Hello, good evening everyone. I hope I am perfectly audible and visible to each and everyone present over here to watch this particular session. Anyway, a warm welcome all of you to the YouTube channel of Infinity Learned by Sri Chaitanya. This is me Surya, your chemistry mentor for this particular session. Finally, we are moving to the final part of this particular chapter, that is redox reaction. Without wasting any time, we will directly go to the topic, that is redox titration. Hi Anish, good evening, good evening. Okay, here the topic is redox titration. Before that, I have a question for you. What do you mean by a titration? What will be the titration? Any idea? What do you mean by a titration? As you can see here in this particular slide, it is defined as the titration is a technique. It is a technique where a solution of non-concentration is used to determine the concentration of unknown solution. This is a technique in which we are using a non-concentration of solution to find out the unknown concentration of solution. And as you can see here, the non-concentration of solution is named as titrant and unknown concentration of solution is termed as titrate. This is very important in the case of titration. Hi Anandu, good evening. Right? Then what will be the titration setup? You can see here this is an image. This is a general titration setup in which this is the burette in which the solution of non-concentration is filled here. That is a titrant. Then the solution to be unknown solution, who is the concentration to be calculated, is taking here in the conical flask. While titrating, while moving this solution from drop by drop, there will be a color change because of the presence of an indicator. Right? Because of the presence of an indicator. We are using an indicator here. For example, if you are considering any acid-base titration, as you can say that acid is always filled in the burette and it is added drop by drop to the conical flask where base is present, and generally phenolphthalein or methyl orange is used as an indicator here, and there will be a color change from pink to colorless. That will be the final acid-base titration setup. Clear? Clear? This will be the general setup for a titration. Now let me move to the basic part, that is the redox titration here. What do you mean by redox titrations? Okay, in the case of redox systems, we are adopting to determine the strength of an oxidizing agent or reducing agent by using a redox sensitive indicator. What is the difference here from the acid-base titration? Here we are using oxidizing agent or reducing agent to find out the strength of unknown solution, right? By using a redox sensitive indicators. Just like phenolphthalein or methyl orange, we are using some other indicators known as redox indicators. Fine? Then, what is the principle behind the redox titration? What will be the principle behind redox titration? As I can say that in the case of acid-base titration, we can say that towards the end point, there will be a color change, right? There will be a color change from phenolphthalein. For phenolphthalein, it will be the color change from, pink to colorless, right? From here, at the equivalence point, we are saying that at equivalence point, all the oxidizing agent will react with reducing agent to form. A final result will be the end point or equivalence point. The principle behind that, the number of gram equivalence of oxidizing agent. The number of gram equivalence of oxidizing agent should be equal to the number of gram equivalence of reducing agent. Clear? Number of gram equivalence of oxidizing agent is equal to the number of gram equivalence of reducing agent. That will be the major principle behind the redox titration. And this is known as the law of equivalence. And in the previous session, I have already discussed about the normality as well as equivalent weight, right? So as you can see here, the number of gram equivalence is equal to the volume into normality. Here it is the volume into normality of oxidizing agent. Then this will be the V2N2 will be the volume into normality of the reducing agent. Clear? This will be the basics of redox titration. Clear? Just let me know. Is it clear? Fine. Now, in this particular topic, we have to discuss about the 3 or 4 types of particular redox titrations. As you can see here, the first one is the permanganometry. What will be the permanganometry? Any idea? What will be the reagent here? Hi, hello, good evening. Okay, what will be the reagent in the case of permanganometry? Any idea? Permanganate. KMNO4, right? That is the potassium permanganate. Yes, that is the potassium permanganate will be the common used chemical in the case of permanganometry. Similarly, in the case of iodometry and iodometry, there is a different type of oxidase redox titration in which iodine is used as the compound, right? Iodine is used as one of the reagent. Then what about dichrometry? K2Cr2O7, right? That is the potassium dichromate is used as a major chemical in the case of dichrometry. Now let me move to the redox titration, that is the permanganometry titration. What do you mean by permanganometry or permanganometric titration? As I already mentioned that the major component used will be the potassium permanganate, right? Potassium permanganate or KMNO4. Then here I am taking an example of redox titration between potassium permanganate and oxalic acid. As we already know that potassium permanganate is a strong oxidizing agent. Strong oxidizing agent. Then what will happen to that? It will undergo reduction, right? An oxidizing agent will undergo reduction. As you can see here, this is the +7 oxidation state. Then it will undergo reduction to form +4, right? +4 or +2? +2, right? It will undergo reduction to +2 state. KMNO4 will undergo reduction to form +7 state to +2 state. And you can see here in the case of, this is the reducing agent used here, that is the oxalic acid. This is a reducing agent. While calculating the oxidation number, you can say that this will undergo oxidation, right? From here H2C2O4 to 10 carbon dioxide, it will undergo oxidation. So this will be the general reaction for the oxalic acid potassium permanganate titration. Clear? Then I have already mentioned that in the case of redox titration we are using some indicators, right? But in the case of permanganometric titration, the potassium permanganate itself is used as an indicator because it is used as a self indicator. It shows colors, that is pink color, right? KMNO4 is used as a self indicator here. This point is very important. Clear? Then, whenever we are adding the potassium permanganate to the oxalic acid, there will be the color change, right? There will be a pink color. And towards the end point, all of the oxalic acid will react with permanganate to form. There will be a light pink color is appearing. That will be the end point or equivalence point of this particular reaction. Right? Then, one more point you have to note that you can see that H2SO4 is present here, right? H2SO4 is present here, which means that the reaction is always carried out in a acidic medium. Most commonly used acid is H2SO4. Instead of, if you are using HCl or any other acid, there will be some distraction in this particular reaction. Clear? Next, the one more point you have to note about the permanganometric titration is that, as you can see here, the +7 state of manganese is changes from +2, right? +7 to +2. Here, Mn2 plus is formed towards the middle of the reaction, right? Mn2 plus is formed at the middle of the reaction. This Mn2 plus is always act as an autocatalyst. What? It is an autocatalyst. It will enhance the rate of the reaction. So we can say that towards the endpoint, the pink color become very high color due to the presence of Mn2 plus because it is act as an octo catalyst. Clear? Fine. Now let me move to the next type of redox titration, that is the dichromatric titration. As I already mentioned that in the case of dichromatric titration, the most commonly used oxidizing agent or reagent is known as the potassium dichromate, right? This is the potassium dichromate, K2Cr2O7. Here I am giving an example of more salt with potassium dichromate titration. As you can see here, more salt is the combination of ferrous sulfate and ammonium sulfate, right? Ferrous sulfate and ammonium sulfate is known as the more salt. And in the reaction, you can see that there is no any particular reaction about the more salt, right? Which means that in the case of more salt, the oxidation is always happen to the ferrous sulfate only. So I am taking FeSO4 in the reaction. Clear? Then here the commonly used oxidizing agent is K2Cr2O7, right? This is the oxidizing agent. It will undergo reduction from +6 to +3, right? +3 stage. It will undergo reduction from +6 to +3. Then this is the reducing agent used here, that is the ferrous sulfate from the more salt. It will undergo, this is Fe+2, right? It will undergo oxidation to Fe+2 to Fe+3. This is the common reaction happen in the dichromatic titration of more salt. Clear? Again, this is also always happening in the acidic medium, for example in the case of H2SO4. Then what will be the indicator used in this particular reaction? Diphenylamine, right? Diphenylamine is one of the important redox indicators which is used in the dichromatic titration. So this name is also very important, diphenylamine indicator. Because of this presence of indicator, after the endpoint or towards the endpoint, there will be a purple color or bluish violet color is appearing. There will be a bluish violet or purple color is appearing. Clear? Is it clear? Or can we move to the third type of titration? Yes. The third type of titration is the titration using iodine, right? I have already mentioned there will be two types of titration including iodine, that is iodometry as well as iodimetry. As you can see here, iodine is always used as an oxidizing agent here. That's why the name comes from the iodometry or iodimetry, because iodine is used as an oxidizing agent here. Now, it is used to determine the strength or concentration of a reducing agent with iodine, right? Then one more point you have to note that in the case of iodine, it is a highly volatile and less soluble in water, right? It is highly volatile and less soluble in water, and it is very difficult to prepare the solution of iodine. So we are taking the solution by dissolving it in potassium iodide solution. So it will form potassium iodide plus iodine to form potassium triiodide. This will be our solution used as an oxidizing agent in the case of iodometry or iodimetry. Clear? Now let me move to the what is the difference between iodometry and iodimetry. Is there any difference between iodometry and iodimetry? I have already mentioned that in the case of two reactions, iodine is always used as the oxidizing agent, right? But what will be the difference? Okay, as you can see here, this is the major difference between iodometry and iodimetry. I have already given in the table as the major points. What is the difference here? This stands for iodometry and this stands for iodimetry. What will be the difference here in the case of iodometry and iodometry? What is the major difference you are seeing here from the table? Okay, here you can see that this is the major difference between the iodometry and iodometry. In the case of iodometry, there is no direct iodine is produced. Only the liberated iodine is used as an oxidizing agent here, right? Then what about the iodometry? There will be the direct iodine is used. There will be direct iodine is used. Okay, in the case of iodometry, as I already mentioned that liberated iodine is used. Why? Because that in the case of this particular reaction, as you can see here, potassium iodide first react with one of the oxidizing agent. Probably, mainly it is used as a sodium thiosulfate as the oxidizing agent to find out the liberated iodine from the potassium iodide. The first step in the iodometric titration is that first the potassium iodide react with any one of the oxidizing agent to produce the liberated iodine. Because Ki, it is in the -1 state, it will first oxidize to form zero oxidation state, right? This is the first step in the case of iodometry. Then what will happen to the second step? The liberated iodine, this is a liberated iodine, right? The liberated iodine react with any of the reducing agent to form I minus. That is the reduction is happening here from 0 to -1. There is a reduction happening here. This is the two reactions happening in the case of iodometric titration. Clear? Yes. Then what will be the indicator used in the case of iodometry? Stars. I think all are familiar with the stars, right? Stars is the indicator which is used in the case of iodine containing titrations. Starch and iodine combine together to form a starch iodine complex which will show us a blue color. Whenever we are adding starch indicator, first we are adding to the liberated iodine, right? Liberated iodine to the reducing agent which is taken in the conical flask. We will just add the starch indicator. While we are adding the starch indicator, it will form a blue color. Towards the end of the titration, there is a color change happening from blue color just disappears. That will be the end point of this particular reaction. Clear? Yes. Then what about iodometry? What do you mean by iodometry? As compared to the iodometry means there is a direct iodine, right? Direct iodine is used as the oxidizing agent here. So there will be only one reaction happening. The direct iodine I2 is reacting with reducing agent where we have to find out the concentration of this particular solution. It will reduce us to, it is 0, right? It will reduce us to form -1, that is minus iodide ion to form the reaction, right? This will be the only one reaction which is happening in the case of iodometry. Then, the same as the iodometry, starch is again used as the indicator here. Then, the same iodine and starch combine together to form the starch iodine complex to form a blue color complex. Towards the end of the titration, when all the direct iodine combined with the reducing agent to form the product, the complete blue color disappears, right? Complete blue color disappears. That will be the end point of this particular reaction. Clear? Ishan, if I try in Hindi also, you will not get any point. That much, my Hindi is not that much good. I can explain English in multiple times, but I am not that much confident with the Hindi language. Is it fine? Did you get the point? What is the difference between iodometry and iodometry? Ishan, yes, I am from South India. Okay, this is about the difference between iodometry and iodometry. Now I will explain the iodometry and iodometry with the examples, right? This is the first reaction, that is iodine with sodium thiosulfate, Na2S2O3.5H2 titration. Here iodine is used as the oxidizing agent, Na2S2O3 is used as the reducing agent here. And I can say that this is a iodometric titration. What do you mean by iodometric titration? Whether it is having direct iodine or liberated iodine is present. Okay, what is the difference between iodometry? What will happening in the iodometry? Whether it is there is a presence of direct iodine or not. Please give me the answer. What do you mean by the iodometry? Whether there is a direct iodine or liberated iodine is present. That is the question. If I start speaking Hindi now, you will make fun of me. I know that. Okay, just let me know what is the difference between iodometry or iodometry. Otherwise, I will say that in the case of iodometry, direct iodine is present, right? Here the direct iodine is present. So here the reducing agent is sodium thiosulfate, right? Na2S2O3 is the sodium thiosulfate, which is the reducing agent used here. As you can see here, while reacting with the direct iodine with the reducing agent sodium thiosulfate, it will form sodium tetrathionate, Na2S4O6 plus 2Na, which means that iodine undergo reduction, right? It is changing its oxidation number from 0 to -1, which means it undergo reduction because iodine is the oxidizing agent used here. Then what about Na2S2O3? What will happen here? While calculating the oxidation number, you can see that Na2S2O3 changes to Na2S4O6 by oxidation, right? By oxidation, because it is the reducing agent used here. Clear? Whenever we are using the sodium thiosulfate with the iodine, it will react with iodine to form sodium tetrathionate to form the iodometric titration. And similarly, here also used as the indicator, that is the freshly prepared starch solution, right? Freshly prepared starch solution. Whenever we are adding sodium thiosulfate from the burette to the conical flask containing iodine, it will form a blue color complex. Towards the end of the reaction, this blue color will be disappearing. That will be the final result of this particular reaction. Clear? Ishan, there is more time now. I will be here till your JEE exams completes. Then I will try to learn Hindi and I will explain in the Hindi also. I will try to explain in Hindi. Don't worry. Then, now let me move to the example with the iodometric titration. As you can see here I am titrating copper sulfate, CuSO4, right? Copper sulfate with iodine. And this is a iodometric titration. What do you mean by iodometric titration? Liberated iodine is present, right? Okay, in the case of iodometric titration, there is the liberated iodine, right? Which means that first any of the oxidizing agent react with potassium iodide to form liberated iodine, right? Liberated iodine. As you can see here, this is a -1 oxidation state. Copper sulfate is used as an oxidizing agent here. This first react with potassium iodide to form the liberated iodine. This will be the first step in the case of iodometric titration. Then in the second step, this liberated iodine, right? This liberated iodine will react with the sodium thiosulfate, which is the reducing agent. Sodium thiosulfate, which is the reducing agent. it will again react to form sodium tetrathionate with sodium iodide. Clear? Which means that in the case of iodometric titration, two steps are happening. In the first step, what will happen in the first step? First, any of the oxidizing agent react with potassium iodide to form the liberated iodine. Then in the second step, the liberated iodine react with the reducing agent to form the I- ions, right? Okay. As in the case of iodometry also, I have already mentioned that freshly prepared starch solution is taken as the indicator, and towards the end of the titration, the color will disappear, right? Blue color is disappears. Clear? Okay, anyway, congrats Ishan to clear the JEE Mains exam. Anyway, thank you for watching my session also. Okay, is it clear now? What is the difference between iodometry and iodometric titration by using different examples? Yes, fine. Now, okay, this is all about the redox titrations. We have discussed about the permanganometry, right? In the case of permanganometry, potassium permanganate is always used, right? Potassium permanganate is used as the oxidizing agent, right? And what about the indicator there? In the case of permanganate or potassium permanganate or KMNO4 itself is used as an indicator because of their pink color. Then towards the end point, yes, I can understand Hindi, no issues. Okay, in the case of permanganometry, towards the end point, that pink color disappears, right? Sorry, the pink color appears. Then what about the dichrometry? Dichromate or potassium dichromate is used as the oxidizing agent there. Towards the end point, we are using the diphenylamine as the indicator there. Towards the end point, there will be appearance of purple or blue-violet color, right? Purple or blue-violet color appears. Then last one is the iodometry and iodometry. In the case of iodometry, liberated iodine is used. In the case of iodometry, direct iodine is used as the oxidizing agent. Clear? Now let me move to the practice questions. One shot videos, right? Which chapter you want for one shots? Anantu? Okay, fine. What will be the answer for this question? In the titration of potassium permanganate versus more salt, the indicator used is, what will be the answer? Option 1, right? KMNO4. I have already mentioned that in the case of potassium permanganate titration or permanganometry, KMNO4 itself used as a self-indicator because of their pink color. Therefore, option 1 will be the correct answer. Clear? So, Nida, it is clear? It is not option C, it is option 1. Then what about diphenylamine? This is a common indicator which is used in the dichrometry, right? Then starch is used in either iodometry or iodimetry. Then what about the methyl red? Methyl red is one of the common indicators which is used in the acid-base titrations. Along with methyl orange or phenolphthalein is also used as the indicator in the case of acid-base titrations. Now, what about this question? When KMNO4 solution is added to oxalic acid, The decolorization is slow in the beginning, but it becomes instantaneous after some time. What is the reason behind that? I have already mentioned that in the case of permanganate titration, for example, in the case of oxalic acid, whenever we are adding KMNO for the oxalic acid, at the beginning of the reaction, there will be the small color change, right? The decolorization is very slow. But at the middle of the reaction or towards the end of the reaction, it will become instantaneous. What will be the reason? Divyansh, option B. What about others? Option 4, right? I have already mentioned that in the case of permanganate titration with the oxalic acid, the oxidation state of KMnO4 changes from +7 to +2, right? Which means there is a presence of Mn2 plus ion. This Mn2 plus ion acts as an autocatalyst which will enhance the whole reaction. That's why the color change is happening instantaneous at the middle of the reaction, right? Which means option 4 will be the correct answer. Is that clear, Divyansh? Okay, fine. Now here is the next question. Okay, this is a little type of numerical problem. Here, 50 ml of 0.02 molar KMnO4 oxidizes 50 ml of potassium iodide solution in faint alkaline medium. What will be the molarity of potassium iodide solution? Option B, right? Okay, what about others? Is there any other options? Option B, right? That is the second one. How we can approach this question? This is a redox titration. In the case of redox titration, it will follow the law of equivalence, right? Which means that the number of gram equivalents potassium iodide, right? What will happen to this reaction? In the case of alkaline medium, I can write here. It will changes from +7 to +4, right? So we are taking here first the volume 50 into 0.02, right? That is the molarity. Then n factor. What will be the n factor here? It is changing from 7 to 4, right? 7 to 4, which means 3. Then here again 50 ml into, what will be the n factor here? We have to find out the molarity, right? So I am taking molarity here. What will be the n factor here? What will be the n factor? N factor means the number of electrons gained or lost during reaction, right? While calculating here, you will get the answer about 0.01 molar. Clear? That is option B will be the correct answer. Now here is the next question for you. The weight of iodine and its molecular weight is already given, that is 254. Required to completely oxidize 1 mole of sodium thiosulfate, 1 mole of Na2H2O3 according to this following equation. It is mentioned that this equation is not balanced, it is unbalanced. What will be the answer? The reaction is already given here. You have to just do the balancing, then apply the mole concept. Okay, what will be the answer? The first step you have to do that, this is the reaction, right? This is already mentioned that it is unbalanced, so you have to balance this reaction. Here only 2 sodium is present, here it is total 2 into 3, right? In order to balance this equation, I will just put it as 2 Na2H2O3 plus 2 NaI, which means that here 2 iodine is present, here is also 2 iodine. Then 2 into 2, 4 sodium is present in the case of left side. And again here 2 sodium plus 2 sodium, 4 sodium. Then 2 into 4 sulfur. Here 4 sulfur, 2 into 3, 6 oxygen, and here also 6 oxygen, which means the reaction is completely balanced now. That is the I2 plus 2 Na2H2O3 gives 2 NaI plus Na2S4O6. Clear? Then here the question is, how much weight of iodine is required to oxidize 1 mole of Na2H2O3? 1 mole of Na2H2O3. As you can see here, 2 mole of Na2H2O3 is required to oxidize 1 mole of iodine, right? Required to oxidize 1 mole of iodine. Right, 2 mole of Na2H2O3 is required to oxidize 1 mole of iodine. Here the question is, how many moles of sodium thiosulfate is required? How many moles of, or how much weight of iodine is required for 1 mole of Na2H2O3? Whenever we are taking 1 mole of Na2H2O3 here, it means 1 mole of Na2H2O3 is required to oxidize how many moles of iodine? 0.5 mole, right? Half of this, 0.5 mole of iodine. Then the molecular weight of iodine is given here, it is 254. For 0.5 mole of iodine, it is equal to 0.5 into 254, that is equal to 127 gram, right? 127 gram of iodine is required to oxidize. Okay, iodine is required to oxidize 1 mole of Na2H2O3. Clear? Option 1 will be the correct answer. Clear? Okay, here is the next question for you. Consider the titration of potassium dichromate solution with acidified more salt using dimethylamine as indicator. What will be the number of moles of more salt required per mole of dichromate? Which means, how many number of moles of more salt is required for 1 mole of dichromate in the case of dichromatic titration? Okay, what is the answer for this question? We have already discussed about the equation of this particular reaction, right? In the case of dichromate. Okay, option 4 will be the correct answer. I will just give the equation here. This is the potassium chromate, right? Potassium dichromate. It will react with the FeSO4 present in the more salt, right? FeSO4 present in the more salt with the acidic medium H2SO4 to form K2SO4 plus Cr2SO4 trice plus 3Fe2SO4 trice plus 7H2. This will be the complete reaction for this particular reaction. And as you can see here, for 1 mole of potassium dichromate, here it is 1 mole of potassium dichromate, right? For 1 mole of potassium dichromate, 6 moles of more salt is reacting, right? 6 moles of more salt is reacting, right? That is the answer for this question also. The number of moles of more salt which is required per mole of dichromate. If you are using only 1 mole of potassium dichromate, it will react with the 6 moles of more salt, which means option 4-6 will be the correct answer. Clear? If you are not remember about the complete reaction, you can just remember this reaction like this. Because dichromate ion Cr2O7 2 minus, it will react with Fe2 plus, right? In the case of ferrous sulfate, it is in the plus 2 oxidation state. Then it will oxidize to form plus 3 oxidation state, right? Fe3 plus, and here it is Cr2, right? Which is in the plus 3 oxidation state. This will be the simple equation for this particular reaction. Clear? Okay, Karthik, which point I want to repeat? The complete question or any of the equation? Okay, in this particular question, the question is how many number of moles of more salt is required per mole of dichromate, which means if you are using 1 mole of dichromate, how many moles of more salt is used in the case of this particular reaction? That will be the question. If you are familiar with the equation, you can write the equation. Just from the equation only, you can get the answers. Otherwise, you can calculate from the n factor calculation. For example, here it is changing from plus 6 to plus 3, right? Plus 6 to plus 3. Therefore, n factor is equal to, for 2 chromium it will be 2 into 3, that is equal to 6, right? 6 will be the n factor. Then what about here? Fe2 plus to Fe3 plus, it is the 1, right? 1 will be the n factor. From the n factor onwards, you can just find out the answers. Just like 6 for 1 mole of FeSO4, it will require 6 mole, right? Clear? Okay, fine. Okay, here is the next question that I think this will be the last question from this topic. What volume of deci normal K2Cr2O7 solution, deci normal K2Cr2O7 solution would be required to convert 119 gram of tin to tin chloride in acidic medium? Tin to tin chloride in acidic medium. The reaction is already given here. This is a dichromate titration. What is the change happening here? Tin is changing from tin chloride, right? Tin is changing from tin chloride. Okay, tin is changing from tin chloride. With the use of K2Cr2O7. Okay, in the previous session when I was discussing about the equivalence point, normality and all, I have just discussed that in the case of potassium dichromate, whenever we are happening in the acidic medium, there is a change that the K2Cr2O7 minus or the dichromate ion changes to form chromate ion, right? Cr plus 3 ion. Because there will be the change like 2Cr3 plus. This will be the simple change. 2Cr3 plus or Sn plus Cr2O7 minus gives SnCl4 plus 2Cr3 plus. This will be the complete reaction here, right? Then what is the change in number of electrons or n factor here? This is from the zero oxidation state. This will be the plus 4. What will be the n factor here? Okay, I am from NIT Calicut. I have completed my post-graduation from NIT Calicut. Okay, what will be the n factor here? In the case of tin to tin chloride. 4, right? Because 0 to 4 change is happening, which means n factor will be the 4. Then what about here? It is from plus 6 to plus 3, right? Plus 6 to plus 3. This change is for only one chromium atom. If you are taking 2 chromium atoms, the change will be 2 into 3, that is equal to 6. 2 into 3, that is equal to 6, right? So simply we are writing the equation that n factor 4 into number of moles, right? N factor into number of moles. Here it is 119 gram of tin. And while calculating the number of moles, you can say that for tin, if I am writing here for tin, the molecular weight of tin is itself 119, right? Therefore, number of moles is equal to 1 mole. For 119 gram of tin means it is 119 divided by 119, that is equal to 1. Right? Number of moles is equal to 1. 4 into 1 is equal to. If we are calculating this normality in terms of volume, we will take it as volume V into normality, right? Where normality is given here 1 by 10. What do you mean by deci normal? Deci normal. Deci means 10 to the power minus 1 or 1 by 10, right? Deci normal. So I am taking here V into 1 by 10 is equal to 4 into 1. Or calculating, you will get the answer as equal to 4 into 10, that is equal to 40 liters. Option D will be the correct answer. Clear? Yes, Anish, you are correct. 40 liters is the correct answer. Clear? Is it clear? Okay, I hope it was clear for everyone. Then, so far we have just completed the complete chapter of redox reactions. We have started from the basis of redox reaction, right? What do you mean by oxidation? What do you mean by reduction? Then we will move into the oxidation number calculation, right? Then finally we move to the types of redox reactions, starting from disproportionation, combination, comproportionation, right? We have studied about a lot of types of redox reaction. Then we move to the normality, equivalence, equivalent weight, law of equivalence, and so forth. Then in the previous session we have discussed about the balancing of redox reaction by using oxidation number method and half reaction method. I hope that things were clear for everyone. Okay, in this particular session we have discussed about the redox titration also, right? Which was the last topic in the redox reaction chapter. Clear? Okay, that's all about from my side for today. Again, there is a gentle reminder about the All India Test Series for the JEE Main session and JEE Advanced 2022. You will get the discount of 2,999 by using this YouTube 50 off code. Just don't miss this opportunity. It is a better opportunity for all of you who is attending the JEE Main session 2 and JEE Advanced, right? Okay, we have completed 2 chapters. Then which topic you have to take on the next sessions? Next day. And tomorrow we will be coming with the practice questions in the particular chapter. You should come along with the practice. You have an idea about the complete redox reaction chapter. Then it will be easy for you to practice all those questions. Okay, I hope all of you guys have enjoyed the session for today. And anyway, thank you all of you. And don't forget to subscribe our channel. Just share this particular session to your friends and family. And also hit the like button for this particular session. Anyway, thank you so much all of you. Good night. Bye-bye. Take care.